Winds, waves, tides, and currents combine to frustrate the efforts of anyone who needs to understand the distribution of plankton in environments like this. Fish larvae are dispersed through the ocean, and as they feed and grow, their increased mobility helps them to escape predators and avoid our nets. The nets used when plankton sampling started some 160 years ago were simple, fine-meshed cones attached to a rigid ring which was fixed by bridles to a towing wall. It was the obvious design and has changed little since then. But 19th century methods don't match 21st century needs. Today, the regulation and conservation of fish stocks is crucial, and recruitment of young fish is a vital concern. In order to understand the complex relationships between variability in the marine environment and the survival of larval fish, we need to be able to gather reliable data. And that means evolving new sampling systems to exploit today's technology. The first developments produced high-speed tow nets and more efficient flow meters like these. Variations of this basic design have been used all over the world. This one is the Gulf 3 or tin tow net. It's an encased net fitted with a flow meter. It's been the standard sampling apparatus for international North Sea herring larval surveys. This is a more versatile multiple net version known as the ocean sampler. But despite these advances, the data that's being obtained is still inadequate. Advances in telemetry and computer-based processing of information offer much more sophisticated techniques to fisheries scientists. That's why, during the past few years, a new sampling system has been developed which can take advantage of them. Faster nets with fewer bridles to alert the larvae. Nets which open and close on command, and which, because of their size, can filter much larger volumes of water. Building on the work and experience of colleagues elsewhere, the scientists at the DAF's Marine Laboratory in Aberdeen have constructed a suite of nets to meet today's demands. They're robust, reliable, have a multi-net capability, and can be opened and closed remotely. They also carry sensor packages which relay information on bottom depth, sampler depth, net function, water flow, and a range of hydrobiological parameters to the towing vessel's computers. This system, for example, can collect over 100 discrete plankton samples and up to 60 water samples for analysis on board ship. While the roof rack mounted sensor system can record, transmit and store a variety of data, its deployment here from the charter vessel Murfak illustrates how compact it is and the ease with which it can be launched and recovered from all sorts of vessels. The method net, being shot here from the Clupea, is a variant of the Isaac Kidd mid-water trawl. It's a large single net with a 5-meter mouth opening, and it's fitted with a depressor. The mesh size is 2 millimeters. There are no bridles to obstruct the net, which remains very stable under tow. This is possibly the largest plankton sampler ever used by any fisheries research laboratory. It's based on a Canadian design and called the Loch Ness. The initials stand for Large Opening Closing High-Speed Net Environmental Sampling System. It consists of 5 nets in a steel framework arranged horizontally rather than vertically. Each net is 14 meters long with a 2.5 meter square mouth opening. The Loch Ness can be towed at speeds of up to 5 knots, and its nets can be opened sequentially by remote control using a through-water acoustic command and telemetry system. It incorporates sensors which indicate depth, salinity, battery voltage, and net status, and transmits their information to the towing vessel via the acoustic link. On board, the data can be displayed in real time on a VDU or stored. Large sampling systems like the Loch Ness and the Method obviously need to be deployed from a vessel fitted with a large crane or a robust articulated A-frame. Their size also requires a large unobstructed stern. To test the system's practical application, sea tests were carried out on Challenger, and they helped to identify several problems. First, The large towing angle, about 60 degrees, meant that the transducers of the acoustic command system weren't properly aligned. Their beam is fairly wide, but the system became unreliable at shallow depths. The next difficulty arose because of poor weather, during which much of the heave at the ship's stern was naturally transmitted to the sampler. This made it somewhat unstable and threatened to damage the towing points. Then the release proved unreliable. And finally, during recovery, when the sampler was lifted clear of the water, there was a tendency for it to rotate around a vertical axis, which increased the risk of damage during the final lift. The extensive testing program enabled the scientists at DAFS to resolve the various problems. This, for example, is an early attempt to deal with the steepness of the wire angle by building on flotation cylinders. They proved inefficient and were subsequently abandoned in favor of two large spherical steel floats bolted together and shackled to the towing warp some 10 meters above the sampler. Another feature evident here is the net hammock, which was added to secure and protect the large nets during the initial stages of deployment. The work of developing and testing goes on. The British Enterprise 3 is preparing to subject this apparatus to a rigorous series of tests sampling herring larvae during a January research cruise in the northern North Sea. Any deficiencies in the equipment or the techniques used to deploy it will be highlighted and corrected as the process of refining and improving sampling techniques continues. It's all part of a research program that's vital to the future of commercial fishing. Critical factors like the relationship between the number of organisms caught in the nets, the volume of water filtered, the distribution of larvae in depth, space and time, and their daily, seasonal and annual variations will be painstakingly analyzed so that the results of these investigations can assist us to further improve the efficiency of our plankton samplers. Over the years, the scientists at the Marine Laboratory in Aberdeen have accumulated unrivaled expertise in the field of plankton sampling. Their energetic, innovative programs continue to refine methods and equipment to meet the needs of an industry which may be centuries old, but which is very much part of tomorrow's world.